As you probably already know, Cypher is the scripting language used in Neo4j, and it's what we have been using already in the previous lectures. In this lecture, we're going to go through a series of basic queries using Cypher with the focus on the data sets that we've already been using. Here's a listing of the basic queries we will go through step by step. So let's get started. To keep things simple, we will be using a text file containing the basic queries, and we'll make this file available for download as a reading in the module. I will briefly review the queries, and then we'll toggle to the browser to view the results of the queries in Neo4j. Neo4j has a very nice feature which allows us to retain individual queries in multiple panels as we're going through the process of exploring each query. So for the first few queries, we'll be using the simple road network dataset that we used in previous demonstrations. And here we have already loaded the dataset into Neo4j. So let's look at our first query. Our first query is a very simple one in which we're counting the number of nodes in the network. So the first line of code simply matches all of the nodes with the label mynode, and it returns a count of those nodes. So let's look at the results. The results are very simple, the value of 11, and we can visually confirm this by inspecting the graph itself and see that it has 11 nodes, and we can see that up here. The next query is almost as simple. We want to count the number of edges. Now, the first thing to keep in mind is in order to count edges, we also need to declare nodes that are associated with those edges. So this first line of code includes a declaration of the nodes associated with the edges. Here we're identifying with the variable r. And then we're returning a count of those edges. So let's take a look in Neo4j. And the results of this query are a value of 14. And once again, we can confirm this visually by looking at our network and counting the number of edges. The next query involves finding all of the leaf nodes in the network. Now, as you may remember from a previous lecture, leaf nodes are defined as those nodes which have no outgoing edges. So notice that we're returning the node represented by the variable m, which is the target node in this query. So here we're matching all nodes associated with edges having the label 2, and we want to place a constraint on those nodes such that they have no outgoing edges. And then we return all of those nodes. So let's take a look at the results. And here we see a single node returned, the node with the label P. And if we inspect our graph, we can see over here on the right the node P, and sure enough, it has no outgoing edges, only one incoming edge. The next query is also similar. We're looking for root nodes instead of leaf nodes. And as you may also remember, root nodes are defined as a node which has no incoming edges. And you may notice that this segment of the first line of code is sort of a mirror image of the same segment in the first line of code from the previous query. We also want to place the constraint on the nodes that we want to return by specifying that they can have no incoming edges. And then we return all of those nodes. When we look at our results in Neo4j, once again we see we only get a single node returned. It's the node with the label h. And if we inspect our graph, we see over here the node h, and sure enough, it has no incoming edges, only a single outgoing edge, which means it's a root node of the network. The next query can be described as a pattern matching query. We're looking for a pattern that we're describing as triangles. This is a pattern that's a bit more complex than the patterns we've been looking for in our previous queries. A triangle can also be described as a 3-cycle consisting of 3 nodes and 3 edges where the beginning and end node are the same. So here we're matching a node A which goes through an edge to node B, which goes through a second edge to a second node C, and through a third edge back to the original node A. And then we return all of those nodes. So let's look at our results. And here we see we have 5 distinct nodes returned, and we have 2 triangles, or 2 3-cycles, from D to E to G, and from D to C to B. And finally, the last query we're going to execute with this data set is going to explore the neighborhood of a particular node, in this case, the node with the label D. And we're going to be looking for what we're calling second neighbors of D. This means nodes that are 2 nodes away from D. So the first line of code matches all nodes that are 2 nodes away from a specific node. And then the second line of code specifies the actual node that we want to consider by constraining its name to have the label D. And then we return those nodes. And here we're using the command distinct because we want to make sure that we don't return any duplicate nodes. All of our nodes must be unique. So let's look at the results. And here we have a network that consists of 9 nodes and 11 edges. And we can see that each node is 2 nodes away from the node D. Some nodes appear to be only 1 node away from the node D, but we can get to those nodes indirectly through another node, which means that they're not only a first neighbor, but they're also a second neighbor. So we encourage you to play around with these queries and make minor changes in them and see what the results might be.